let's go through the first example in our lecture once again. We have been tossing a coin 1000 times, and 458 times we obtained eagle. The question was, is this a fair coin? Is this a symmetric coin? We have a scheme of testing of statistical hypotheses. The first thing we did was to formulate two hypotheses. The first hypothesis, the so-called null hypothesis, was that the coin is fair. H0 or null hypothesis is always a hypothesis, nothing is going on. So our H0 was, there is no problem, the coin is fair. The alternative hypothesis was that the coin is not fair. It means it has some wrong prediction of frequency of occurrence of the eagles of the two sides of the coin. Now, at point 2, we had to decide what could be modeling our situation. And if we assumed that we were dealing with a fair coin, then the experience of 1000 tossings could be modeled by binomial distribution with parameters 0, 5, and n equal 1000 and p equals 0, 5. 0, 5 denoting probability of success in one tossing, in one throw, and probability of failure this way is also a half. Now, we of course notice that we have very many occurrences, very many trials. So in this case, the binomial distribution might as well be modeled by normal distribution with parameters mu and sigma squared. Mu is mean, and the mean is the same as in the binomial, which is NP. So in our case, that was 500, and variance was the same as previously, so that was NPQ, so we obtained 250. Okay, next step was to find or to choose the level of certainty we want to use in our investigation. Well, before that, a type of test. We were not we didn't have a hypothesis that the coin favorized eagles or the favorized heads. We didn't. We just had hypothesis. It's not fair. It's skewed to left or right, but anyway, it's not fair. The probability is not 0.5. So if you look at this diagram, that meant that we assumed the mean was not as expected, but a little bit more or a little bit less on the two sides. So we had two critical regions for that, either too big or too small, the two blue regions on the left and right. And it's easy to see that means the region begins when the probability of being below this star on the right is equal to 1 minus alpha by 2. So the point where the right star is at 1 minus alpha by 2. So we have inverse of the distribution function of standard normal, and we obtain the critical value. So the critical region has practically two infinite intervals on the left and on the right. Now, what is the next? We have to find at the given alpha, we have to find the critical region. And what can be said about the critical region? If you remember our example, we found the z-score of our results, and the z-score occurred to be very, very low, and they fell into the critical region, which for alpha equals 0.05 started at 1.96 and below minus 1.96. Anyway, the result we obtained was in the critical region. But a natural question is, how about this critical region? How about significance level? What does the significance level practically mean? The significance level 005 practically means that the result we have obtained experimentally might occur even though the coin was fair. So probability of this occurrence is 0.05. So if you want to be sure that it's not by chance, then why not take a smaller alpha? Well, let's observe the critical regions for different values of alpha. The yellow region is for significance level 0.10. And the z-score at this moment is plus minus 1.65. Okay, our results were for alpha equals 0.05. So this is a little bit wider than this, both on the left and on the right. What happens if we go to even smaller level of significance? Then the regions on the left and on the right become even smaller. They are very dark red and very dark blue. Okay, so then what happens? The probability that the result that we have obtained was by chance is very, very small. But it reminds a situation when a girl is very uncertain of the love of her boyfriend, and she puts him to trial, and the trials becoming more harsh and harsh. For example, she asks him to call her every hour, to send messages, to buy flowers, and to do a lot of things which finally would make everyone impatient. So if you really want to be sure, you will make a mistake. You will exaggerate. You may exaggerate. So let's observe the situation on a diagram. There are two types of mistakes we can make in a statistical testing. There are two possibilities for H0. Either H0 is true or it is false. I hope everybody agrees. And at the same time, there are two types of decisions a scientist can make. Either he rejects H0 or he does not reject H0, and he says we cannot reject H0, it might be true. Okay? In two cases, the decision is right. It is when the H0 is false and we reject it. That's a very good decision. Another good decision is when H0 is true and we don't reject it. But it may happen that H0 is true, but we reject it. It's like the boy who really loves the girl, but she rejects this love. Maybe she has too much demand. It's like you want a too high level of significance. This is called the error of the first type. It's called falsely positive. And alpha represents this error of the first type. Now, the second wrong decision would be when H0 is really false, but we don't reject it. And this is error of the second type. And this is falsely negative. And we denote it by beta. Let's have a look at the diagrams. What is the relationship between those two errors? Let's consider two populations. They differ a little bit, and we are testing them. Let's assume that we take alpha equals 0.05. if alpha is marked by red, at this moment the chance for making beta error is marked by blue. What happens if we make alpha smaller? Then there is more space for beta error. Okay, so it seems that we cannot push the limits too far. The more certain you want to be of your result, the bigger the chances that you will make the beta error, that you will not reject null hypothesis, although it is true. Okay, next thing is, imagine two populations which really strongly differ. Then, if they differ very much, then even at the same level of significance, the probability of beta error is much smaller. Now let's speak about the power of the test. This is probability of not committing the error of the second type, of not rejecting null hypothesis, when in reality it is false. The bigger this probability, the better is the test as a tool for differentiating between the false and true hypothesis. The power of the test might be expressed as complement of the probability of making the error of the second type, which means 1 minus beta. The power of a test depends on the following factors: on the number of elements in the sample used in the test, of the real size of effect in the populations, and on the level of significance assumed. Most of the times we assume 0.05. How can we enlarge the power of testing? The most important thing is to enlarge the sample, especially by pilot investigations. It means you take a smaller sample and you test it to see if any effect is visible or not. Of course, some tests are better for certain situations, some are worse, so we should take as good test as possible. We'll be speaking about it later. And of course, we should be using tests or structures of investigation which have, by their nature, higher statistical power. Okay, and that will be all for today. Next time, I would like to make a smaller overview and examples of statistical tests and give as many examples as possible.